The central danger of concurrent programming lies in unsynchronized access. When multiple parallel threads attempt to read and write to the exact same space in memory simultaneously, they collide. This creates a data race, leading to unpredictable behavior and memory corruption. Rust solves this problem without relying on a heavy runtime garbage collector. It achieves what is known as fearless concurrency by enforcing strict memory access rules entirely at compile time. To give developers flexibility, the Rust standard library provides two distinct architectural paradigms to handle safe parallel execution: message passing and shared state. This split screen illustrates two philosophies. On the left, message passing. Data physically moves through mpsc pipelines, flowing linearly from one thread to another. On the right, shared state. Data remains stationary. Threads take turns accessing it using architectural wrappers like Arc and Mutex. Both systems rely on Rust's ownership and type system to regulate access. These rules allow the compiler to identify and block potential thread collisions while the code is still being built. Looking closer at message passing, mpsc channels act as one-way linear data pipelines. Instead of threads trying to share the same piece of memory, one thread simply hands the data off to another. This code snippet shows the basic channel instantiation. Calling the mpsc channel function returns a tuple containing two halves, a transmitter, assigned to the variable tx, and a receiver, assigned to rx. The acronym mpsc dictates the specific architecture of this pipeline. You can have multiple transmitting nodes sending messages, but they all feed into exactly one single receiving node. To push data down this pipeline, we call the send method on the transmitter. But to execute this inside a spawned thread, we must explicitly use the move keyword on the closure, drawing the target variable into the thread's environment. The immediate consequence is that send takes absolute ownership of the value. Once the data enters the pipeline, it belongs to the receiving thread. If the original thread attempts to read that variable afterward, the compiler intervenes, throwing a borrow of moved value error. By revoking access from the sender, the strict transfer of ownership physically eliminates the possibility of a data race. The original thread simply cannot corrupt memory it no longer owns. To leverage the multi-producer capability, you can call tx.clone. This generates a new identical transmitting handle that can be moved into a completely separate parallel thread, allowing multiple sources to feed the same pipeline. On the receiving end, the standard method to extract the data is receivo. Calling this method blocks the main thread's execution entirely, pausing the program until a message successfully arrives down the channel. Alternatively, you can use try-receive. Rather than blocking execution, this method returns a result type immediately, yielding the data if it's there, or an error if it isn't. This allows the receiving thread to perform other calculations instead of idling. mpsc channels bypass complex synchronization requirements entirely. They ensure safe concurrency by turning data transfer into a strict zero-sum exchange of ownership. But not all architectures can rely on one-way pipelines. Some systems require multiple parallel threads to synchronously access the exact same piece of centralized memory. To safely manage this shared state, Rust requires a gatekeeper, the mutex, short for mutual exclusion. A mutex enforces a single, unbending rule. Before a thread can read or write the underlying data, it must signal its intent and successfully acquire exclusive access to the lock. Only one thread can hold this lock at any given moment. In many historical programming languages, mutexes are notorious for causing deadlocks. Developers must remember to manually release the lock when they finish processing. If they forget, every other thread waiting for that data is frozen permanently. In this code snippet, we create a new mutex holding the integer 5, and then call .lock to access it. Rust prevents manual locking errors by changing what this method actually yields. Calling lock returns a mutex guard smart pointer that wraps the underlying data. Through the dereference operator, the thread reaches inside this protective shell to mutate the value. When the variable goes out of scope, the drop trait triggers, automatically releasing the lock. The lock method also returns a result type to handle what's known as poisoning. If a thread panics while holding the lock, the mutex enters an intentional failure state to prevent other threads from accessing potentially corrupted data. By binding the release of the lock to the physical lifecycle of the mutex guard variable, the compiler completely automates away the human error of forgotten locks. A mutex safely gates memory, but a scaling problem emerges when you try to share that single mutex across 10 different spawned threads, perhaps to increment a common counter. If you inject the raw mutex into a loop of closures, this terminal output shows a compiler rejection stating use of moved value. You can't move the same mutex into 10 different threads because the first thread takes total ownership of it. The strict one-owner rule is blocking us. The mutex needs to have multiple simultaneous owners for the threads to share it. A logical attempt to fix this is wrapping the mutex in an RC, or reference-counted smart pointer, which allows multiple variables to own the same data by keeping a running tally of active references. But the compiler rejects this as well. This error shows that RC cannot be sent between threads safely. Its internal tally counter isn't thread-safe, meaning two threads could try to update the reference count at the exact same millisecond, causing a data race on the pointer itself. To safely distribute ownership across multiple cores, we need the thread-safe equivalent, the ARC, or Atomic Reference Counted Smart Pointer. The term atomic means that the pointer's internal operations cannot be interrupted. It guarantees that reference count updates are perfectly sequenced across multi-core processors. The core data sits at the center, wrapped in a mutex, encapsulated by an outer ARC layer. This ARC layer allows multiple threads to legitimately clone the pointer. The inner mutex lock provides interior mutability, safely allowing threads to modify data one at a time. By default, the ARC smart pointer only provides immutable access to the data it holds. The mutex nested inside is what safely bypasses this restriction, combining shared ownership with exclusive mutation. This nested type structure provides the evidence needed to verify that every thread has a valid, synchronized path to the data. It proves to the compiler that memory is shared safely. Stepping back, these two concurrency tools are distinct, practical engineering choices, each suited to different architectural needs. This matrix outlines the division. mpsc channels transfer discrete ownership down a pipeline, ensuring data only ever has one valid owner. Alternatively, an ARC mutex handles centralized shared state, utilizing strict lock queues and atomic pointer counting to gate the resource. Rust's concurrency guarantees do not rely on a hidden runtime engine watching your program execute. They rely entirely on strictly enforced structural rules, traits, and smart pointers mapped out during compilation. However, there is a limit. Rust guarantees prevention against data races and memory corruption, but it cannot mathematically prevent logical deadlocks, such as two parallel threads permanently waiting to acquire each other's locks. Fearless concurrency focuses on preventing data races and memory corruption. By eliminating these specific categories of errors at the compiler level, you are left to focus on the logic and structure of your application.